somber, dramatic tone, visuals of Cold War USSR, snowy Arctic islands, scientific labs in the annals of human engineering. Few projects rivaled the audacity of the Tsar bomba. Officially designated RDS, this device represented the apex of nuclear weapon design, a synthesis of physics, materials, science, aeronautical engineering, and detonation mechanics. With a yield of 50 megatons, it remains the largest explosive device ever detonated. Today, we examine not only the scale of the Tsar bomba, but the incredible engineering feats required to bring it to life. Since 1961, the Cold War had entered its most perilous phase. Nuclear parity was central to global strategy. While the United States and the Soviet Union both possessed thermonuclear weapons, the Soviets sought a demonstrative divisive bomb that would embody raw power, unrestrained by tactical utility. The Tsar bomba was never intended for deployment in combat. Its primary purpose was a geopolitical signal, an engineering marvel beyond conventional understanding, designed to project invincible technological capability. The Tsar bomba was a three-stage thermonuclear device. At its core, the primary stage utilized conventional fission to initiate extreme temperatures and pressures. This energy then compressed and ignited the secondary fusion stage, consisting of lithium-6 deuteride, which underwent nuclear fusion, releasing exponentially more energy. A tertiary fusion layer, largely unprecedented in scale, added an additional amplification of explosive yield. Critically, the design incorporated a lead tamper in place of uranium-238 to reduce radioactive fallout and intentional engineering compromise, prioritizing a controlled test over maximal radiation output. Diagrams of bomb casings, fuel assemblies, and explosive lenses. Each stage required specialized materials capable of withstanding extreme conditions. The fissile core of the primary stage contained highly enriched uranium, carefully machined and shaped to precise tolerances. Explosive lenses surrounding the core ensured symmetrical implosion, critical for uniform compression. The secondary stage required lithium-6 deuteraide crystals enriched to exact specifications. All components were housed within a steel and aluminum casing, engineered to survive aerodynamic stresses and temperatures during freefall. Every component's mass, density, and thermal conductivity was meticulously calculated to achieve proper detonation sequencing. The Tsar bomba weighed 27,000 kilograms and measured 8 meters in length. Delivering such a payload demanded a modified 295 bomber. The aircraft required reinforced bomb bays, weight reduction modifications, and shock-proof avionics to withstand the extreme proximity to detonation. Engineers calculated optimal release altitude, free fall trajectory, and escape velocity. The bomb was fitted with a stabilization parachute to slow descent, providing sufficient time for the bomber to retreat approximately 45 kilometers. Before detonation, an operational engineering solution to protect the delivery platform from the massive blast. The Tsar bomba's detonation involved sequentially timed nuclear reactions. First, the primary fission charge compressed the secondary fusion stage through X-ray flux generation. Secondary fusion produced temperatures exceeding 100 million Kelvin, initiating tertiary reactions. The resulting fireball reached a diameter of approximately 8 kilometers within milliseconds. The thermal pulse extended hundreds of kilometers, capable of causing third-degree burns at extreme distances. The shockwave, propagating supersonically through the atmosphere, circled the globe multiple times, demonstrating energy release equivalent to 50 million tons of TNT. Structural analysis of this blast informed both civil defense studies and subsequent nuclear designs worldwide. Footage of scientists' calculations on blackboards, lab experiments. Constructing a device of this magnitude presented unprecedented challenges. Precise timing of explosive lenses was crucial. Microsecond deviations could preempt or disrupt detonation. Thermal expansion under extreme conditions required compensatory allowances in casing design. Aerodynamic stability of the bomb, combined with minimal risk to the delivery aircraft, demanded advanced parachute systems and trajectory modeling. Material tolerances were pushed to their limits. Every weld, fastener, and structural member was engineered to survive immense forces while maintaining alignment of fissile and fusion components. The Tsar bomba was, in every sense, a feat of mechanical and nuclear precision. On October 30th, 1961, over Novaya Zemlya, the Tsar bomba was deployed. The detonation produced a fireball 8 kilometers wide, a mushroom cloud 60 kilometers high, and a shockwave that circled the Earth 3 times. Seismographs worldwide recorded it as a magnitude 5.0 earthquake equivalent. Observations of thermal radiation, blast propagation, and atmospheric effects provided invaluable data for nuclear physics and aerodynamics. Engineers meticulously documented each parameter, from gamma radiation levels to the structural response of distant ice formations, offering unprecedented insights into high-yield nuclear detonations. Montage of nuclear research, global treaties, tsar bomba models. The tsar bomba was never intended as a practical weapon. Its yield, delivery constraints, and sheer size made it strategically impractical. Yet, from an engineering perspective, it stands as a singular achievement: the careful orchestration of nuclear physics. Materials, science, aerodynamics, and explosive engineering on a scale never before attempted. Its legacy is a reminder of both the potential and the peril of human innovation. The tsar bomba was an unparalleled exercise in technical audacity, and its lessons continue to inform physics, engineering, and global policy to this day. Fade out with slow zoom on mushroom cloud, reflective music,